All right, so let's work on these two guys. The first one, first of all, they're both cantilevers like the previous two, but you can see the load has increased. So we had a point load, now we had a bending moment. Now we're going to have a uniform load, uniform load, and then we're going to have a linear varying load. So again, just to get this process started, I'm going to tell you that the resulting reaction force is up and equal to the area under that, which is W naught over L, and that the resulting moment is in this direction and is going to be W naught L squared over 2. I'm sure if I gave you more time, a minute or two, you'd be able to come up with those values from this loading. And just to give you a little help with seeing that, remember that the concentrated equivalent force is the area of the curve, base times height, that's W naught L, and that the distance to the centroid is half the distance, which in this case would be L over 2. And you can see the reaction moment is just W naught L times L over 2, and that would give you W naught L squared over 2. All right, so now we're going to start with our shear diagram. And remember, we're going to use the relationships that we've already talked about. The change in shear is going to be the area under the load curve, and the slope of the shear diagram is going to be given by the value of the load. First, let's talk about what do we know the shear to be at the beginning of the beam? Okay, this is a shear force. Is this positive shear or negative shear? Positive. So we're going to start at a positive shear value of W naught over L. What's the shear force at the end of the beam? 0. So you can imagine just taking a smaller and smaller and smaller and smaller and smaller and smaller slice. So if you get so small that what? There's no load left. It's different when you have a point load, because that point load exists at a point, and you never really get past the point load. So that's why, if you might remember our previous problem, we had a point load of P here, we had a shear of P at the end. But now we know it's 0. So the change in shear is the area in the load curve. So I look up at the load curve, and look, it's nice and continuous over the whole length. And what's the area under that curve? We've already found it, right? It's the equivalent force. So this is W naught L. And that force is positive or negative? What kind of sign is a force acting down? Negative. So if I start at WL and subtract WL, I do in effect get 0. So that's satisfied. And what's the shape of the curve in between? Well, the slope is given by the loading, and every point you look on this beam in the shear diagram, what's the value of the load? It's constant, and it's negative W naught. So it's a negative slope. It looks like that. So again, the slope would be 1 W naught. And now we have a triangular or a linear shear diagram. So we started off with a constant load, and we've basically integrated that, and now we have a linear shear diagram. So now to do the moment, we're going to apply that the change in moment is the area under the shear diagram, which we've just built, and that the slope of the moment diagram at any point is given by the shear, which we've just built. So this is one thing that is kind of a little dangerous about these problems, is if you incorrectly build the shear diagram, then you are definitely going to incorrectly build the moment diagram. So anytime you know values of shear force and bending moment, that really helps you match up your graph and give you some sense that you're successful. So now looking at the moment diagram, do we know the bending moment anywhere? Well, we always like to start on the left side. Do I know the bending moment there? Yes. Yeah. Is this a positive or negative bending moment? Negative. It's negative. So that means we're going to start off at negative W naught L squared over 2. What's the bending moment out here at the free end? 0. Now let's see if our relationship between shear diagram and bending moment diagram is satisfied. So it says the area under the shear diagram should be the change in the moment. So the change in the moment from here to here is positive, W naught L squared over 2. And then what's the area of this curve? Well, it's a rectangle. It's a triangle, so 1/2 base L times height, W naught L, and that's a positive area. And you get exactly the same thing. You get W naught L squared over 2, which you add to negative value, and you get 0. So that works. What's the shape of the graph? What's given by the shear? Now, a quick look at the shear diagram shows the shear value is changing constantly. What would be the shear value right here at the beginning point at x equals 0? It would literally be W naught L. And that's a positive or negative slope? It's positive because the shear value is positive. So I'm going to draw a positive slope beginning here. And that slope is going to decrease all the way down to what value here at the end? 0. What kind of slope is 0? That's a horizontal line. So with just those two end conditions, it'll give you the ability to kind of sketch the rough shape of the graph. Now, you're not going to get the exact shape. That's why this shear force and bending moment diagram is an approximation. So you're going to get something that looks like that. And there's the rough shape of your moment diagram. Now, you might ask yourself, well, wait a minute. We could easily write this as an equation and get the shear and moment. And I have an equation for moment. I could find the moment everywhere I wanted. Yes, you could. But where's the most critical value for moment? The maximum. Does our graph identify what the maximum value is and where it occurs? It does. So sometimes this graphical technique will give you the information that you want. If you want to know the moment right here, it's going to be a little trickier. You still can do it with these relationships, but you might want to think about going back and writing the moment equation if you really wanted that. This is another interesting thing, too, is usually the shape of the moment diagram, if you want your beam to be equally stressed throughout, then your beam should have a shape similar to the moment diagram. So think of a beam being very deep with lots of capacity at the beginning, and then the beam tapering to a very narrow or very shallow depth out here at the end where the moment's near 0. So you might see a lot of tapered beams that might have some shape like this. And this shape was really derived from the moment diagram. All right, let's keep this going. So let's apply the same techniques we've done here to this linear varying load. So just to help me with this, I'm going to go ahead and compute my concentrated equivalent force, which will be the area under this curve. It's a triangle, so it'll be 1/2 base times height. So that's going to be W naught L over 2. And what's the distance from the support to the centroid? Yeah, 2/3 of L. 2L over 3. So our reaction force is going to be equal to the concentrated equivalent, which is going to be W naught L over 2. And our reaction moment is going to be equal to that force times the distance. You can see the 2 in the numerator and the denominator cancel, and you get W naught L squared over 3. So now let's start and let's build our shear diagram. So what's the value of the shear as we start here on the left side? Well, it looks like the value is W naught L over 2. Is that a positive shear or a negative shear? Positive. So we're going to start at positive W naught L over 2. What's the shear at the free end? We talked about that before. It's 0. So the change in shear over this length L, change in shear, is given by the area of the load curve. And what's the area of this load curve? Well, we've already computed it. It's right here. It's W naught L over 2, or 1/2 base times height. And what kind of load is that? Positive or negative? Negative. So I'm going to start at positive W naught L over 2, and then subtract W naught L over 2, and I do in effect get 0. So that checks. And what's the shape of the curve in between? Well, the shape or the slope of the shear diagram is given by the load. So let's see what the load is. So starting here at x equals 0, what's the value of the load? 0. So I'm going to start at 0 slope. And the slope progressively gets bigger to a maximum value right here at the end. And that load is positive or negative? Negative. So that means I'm going to end up with a big negative slope at the end. So now I'm going to fit a curve that matches those slopes and get something like that. And again, the shape of this is not that critical. You should get roughly the shape. But again, you can see, can I identify a maximum value for shear? Sure, it's right there. And I can also find its location. So this is a linear line. So through the integration, this is what order line is this? Second order, it's quadratic. So we're going to integrate that to get the moment. So what order should my moment diagram be? It should be cubic. And here's where you start to run into a little bit of problem with this analysis. Let's start to build a moment diagram using the shear diagram. So starting here on the left side, do I know what the bending moment is? Yeah. W naught L squared over 3. Is that positive or negative? Negative. So I got W naught L squared over 3. And then what's the moment at the free end? 0. So really, I kind of know what I've probably already got, so I'm in pretty good shape. Now, the change in moment here should be given by the area of this curve. Now, that's where it gets a little tricky, because most of you probably don't remember the general area of a parabolic curve. It just happens to be 2 base times height over 3. And in case you don't remember that, if you have a book, electronic or paper, and you look inside the back cover of the book, you'll see the general area and centroid of what's called a parabolic section, and then its corresponding rectangular piece called a spandrel. And these are both the parabolic version, the second order version. And you can see the area is 2/3 base times height. We don't really need to remember where the centroid is right now, but it's there. In fact, they even have the same thing for any in-order curve. Cubic, quartic, quintic, all the way up. I'm not going to remember those, and I don't expect you to do either. But if you do get in a jam at home and you need to know something like that, there it is. And also there's the centroid for the trapezoid section if you ever wanted to work that as a solid.
Do we have to know this for the test too?
No. I just wanted to show you that to give you some idea that typically when you see these triangular loads and you're trying to construct the shear force and bending moment diagram graphically, you're probably going to have some issues when you get to the moment diagram. Now, one thing that helps us this time is this is truly a parabolic section. Now, what is that's defined by? Well, one end or the other has basically a 0 slope, or a slope that's vertical. If I wanted to find the area under just a simple segment of it, like say, hey, I don't even want that much of it, well, then it gets a little tricky. Or if I want that side, you can see that that's not a 0 slope, and so it's harder. Now, if I have an equation for the load, obviously I can integrate it and find whatever I want. So you might have to, on some problems, go back and actually write the shear force and bending moment equations like we did last week, and then just simply plot them. Let's see if we can soldier through and get this one. So, knowing this 2/3 base times height, then what you'll get is height, W naught L squared over 2 times base L times 2/3. And if you compute that, it's positive, and it's equal to W naught L squared over 3. So this was negative. We're going to add that positive here. We do get to 0. And what would be the shape of that curve? Well, the slope of the moment diagram is the shear. What's the value of the shear right here at the beginning? It's a positive number, right? So we start off with a positive slope. And the value of the shear decreases to, what's it here? 0. So we know that the slope here at the end is 0. So that should give you enough to kind of give you a rough idea of how to draw the shape of the moment diagram. All that said, where's the maximum moment occur? At the fixed connection, and we know the value. Where's the maximum shear occur? At the fixed connection, we know the value. That's very typical of cantilever sections. The maximums are going to occur at the support. So now that we've done a few of those, let's try some simple supported beams.